So, I mean, we multiplied the series by 1, and a lot of stuff canceled out, leaving us with this. Now, this process of canceling things out is known as a telescoping sum. Right, imagine those old-time pyrotelescopes which collapse upon themselves. That's the idea here. Very nice descriptive term. And now, as n goes to infinity, what is happening to 1 over 2 to the n plus 1? Well, as n goes to infinity, 2 to the infinity is infinity, 1 over infinity is 0. This term is going to go to 0. In other words, the limit of Sn as n goes to infinity, which is the limit of 1/2 minus 1 over 2 to the n plus 1 over 1 minus 1/2, is just, right, this thing goes to 0, so you get 1/2 over 1 minus 1/2, which is exactly 1. As predicted, right? This series converges to 1. Take a step back and ask yourself, what does this sequence of partial sums actually do? It redefines a new object. It redefines series in terms of something you're already familiar with, namely sequences. So everything you know about series, or rather everything you know about sequences, now applies to series. In other words, if you have two sequences that converge, you can add them together, and you get a new convergent sequence. The same is true for series, because a series is really just a sequence of partial sums. If you have a convergent sequence and you multiply by a number, you get a new convergent sequence. The same is true for series. Let's take another example. Consider the series negative 1/3 to the n. We're going to work out the sequence of partial sums again. S1 is the first term, which in this case is 1. S2 is the sum of the first two terms. So when n is 0, you get 1, plus when n is 1, you get minus 1/3. S3, the sum of the first three terms. 1 minus 1/3. When n is 2, you get plus 1 over 9. And so on and so on. Sn, can we describe Sn? 1 minus 1/3 plus negative 1/3 squared, going all the way to, you're going to have n terms here, you're starting at 0, so minus 1/3 to the n minus 1. Convince yourselves that it stops at n minus 1, giving you the required n terms. Let's repeat the same idea as before. We're going to multiply Sn well, why don't I call this, why don't I write it like this? I'm going to multiply Sn by a good number. I'm going to multiply Sn by 1, but a nice representation of 1 so that a lot of stuff cancels out as we did before. What are we going to multiply Sn by? 1 minus negative 1/3 over itself. Observe what happens here. If we multiply every term by 1, and so on, all the way to, and then multiply by negative 1/3, so plus negative 1/3 plus negative 1/3 squared, all the way to negative 1/3 to the n. The whole thing over 1 minus negative 1/3. And again, you have this telescoping sum idea. Sorry. I've made a terrible mistake here. I was supposed to subtract. So minus this times 1. This is a minus here, as we had before, right? These are all minuses. It's a bit hasty there. And now you see that things cancel, right? Negative 1/3 minus negative 1/3. So these cancel out. Negative 1/3 squared minus negative 1/3 squared. These cancel out. Everything cancels out, including the negative 1/3 to the n minus 1, because the term that comes before negative 1/3 to the n is exactly negative 1/3 to the n minus 1. So that's going to cancel with this last one, leaving you, again, right, you have this telescoping sum idea, 1 minus negative 1/3 to the n over 1 minus negative 1/3. And as n goes to infinity, again, this goes to 0, right? Because this is really so if you look at the limit of Sn, which is 1 minus negative 1/3 to the n over 1 minus negative 1/3. The only thing that depends on n is this, and that's going to go to 0. You can prove that with relative ease, maybe using the squeeze theorem. I'll let you work that out. And as n goes to infinity, this converges to 1 over 1 minus negative 1/3, which is really 3 over 4. So sequence of partial sums converges to 3/4. The series converges to 3/4. Can we generalize? Can we do this in general? Right? What are we doing here? We were adding powers of a number. Fix a number A that is different from 0. What is that? What is that series? It's 1 plus A squared plus A cubed, and so on and so on. Let's work out the sequence of partial sums. First term is 1. S2 is the sum of the first two terms, 1 plus A. S3, the sum of the first three terms, 1 plus A squared. In general, where are we stopping? 1 before the index. Sn is 1 plus a squared all the way to a to the n minus 1. Let's do exactly what we did. Let's multiply Sn by a good representation of 1 so that a lot of stuff cancels out. Maybe we get a telescoping sum if we choose the right form. What are we going to multiply Sn by? 1 minus a over itself. Here, I'm assuming a is not 1, so a is not 0 or 1, because you don't want to multiply by 0 over 0. And what happens if we multiply by this? Well, let's multiply by 1 again. So you get this whole thing, and then minus a squared all the way to minus a to the n. And the term that comes right before is a to the n minus 1, so why don't we write it like this? Only to understand what's going to happen. And the a's cancel. The a squares cancel, everything cancels, except the first and last terms. Now, if a is between -1 and 1, if a is some fraction between -1 and 1, this a to the n is going to go to 0. If a is less than 1 in absolute value, this is going to be a fraction which goes to 0 as n goes to infinity. So if a is between -1 and 1, this is going to converge. If a is outside of that interval, if a is bigger than or equal to 1, think about what's happening here. You're going to be adding numbers that are bigger than or equal to 1 infinitely many times. No hope of convergence, you're going to get infinity. If a is a number less than or equal to -1, you'll be alternating between large positive numbers and large negative numbers, and you're not going to get a limit. So the limit of Sn, if a is less than 1 in absolute value, is 1 over 1 minus a. This is such an important series that we give it a name. Definition. The series a to the n is known as a geometric series. The series converges to 1 over 1 minus a if a is less than 1 in absolute value and diverges otherwise.